Today we're going to be talking about derivatives of inverse functions and the derivatives of inverse trigonometry. So for this first example, we want to find the derivative of the inverse. So first we have to find the inverse. So we switch x and y. And now what we want to do is we want to try and solve for y. Now this example, it's going to be really hard to try and solve for y. So let's use our implicit differentiation to then find the derivative with respect to x. So I find dx of both sides. Now remember, the derivative of x with respect to x is 1. The derivative of y cubed with respect to y, with respect to x, is 3y squared dy dx. And so on. Now I factor out all of the dy dx's, and so we get dy dx to be equal to 1 over 3y squared minus 6y minus 7. Now I want you to notice a few things here. Notice how our derivatives all in terms of y, but also if we were to look at the derivative of the original function, so there's our derivative of the original function. How are these related? Well, isn't this 1 over the derivative of the original function, but now with the inverse or the y's put in? Okay? That's super important for us to understand. Now the reason why this is derivatives of inverse functions. So I have my original function, and I have my tangent line, and then we have our inverse. Remember that these slopes are reciprocals because our original and our inverse are reflections across the line y equals x. So therefore, when I find the derivative of the inverse with respect to x, evaluated at f of a, or what was y in our original function, that's equal to 1 over our original function evaluated at a. Or put another way. And this kind of combines the two pieces of what we've been talking about. So we have a function that is differentiable and 1-to-1 on this interval. And the inverse is also differentiable. And the derivative of the inverse is 1 over the derivative of the original function, evaluated at the y points of the original or the x points of our inverse. Okay, now, derivatives of inverse functions. This is also important. This is how we can tell whether or not a function is differentiable if the inverse is 1-to-1 and differentiable. So if a function is differentiable at every point on an interval and the derivative is never 0, so that's what this here means. The derivative is never 0 on that interval, that f has an inverse, then our function has an inverse. and the inverse is differentiable. So I have an example where this is not true. We have y equals x squared. So we know this function is not 1 to 1. Because it doesn't pass our horizontal line test. Remember, the horizontal line test told us whether or not a function was 1 to 1 or if the inverse was a function. So now looking at the derivative, which is the line y equals 2x, when I look at this line, it means that our derivative is never 0. This derivative is 0 right there. Why is that? Because our y equals x squared function was decreasing, or these slopes were all negative. The slopes were all negative, and then we changed to increasing, or the slopes ended up being positive. Okay? So when a function changes from decreasing to increasing, it's not going to be 1 to 1. Thus, our derivative is going to change from negative to positive, and we're not going to be able, we're going to tell from our derivative that the original is not a 1 to 1 function. Our next example. We want to show that our function is 1 to 1 and has a differentiable inverse. So we're going to use that theorem that we were just talking about. Let's look at the derivative of our function. The derivative of this function that's the derivative of the function. Now I need to show that this is always positive, so I set it equal to 0. I eventually get x squared equal to negative 1. X squared, that could never happen. X squared can't be equal to negative 1. So therefore, since f prime of x is greater than 0, f of x is 1 to 1 and has a differentiable inverse. Now let me find f of 1. So when I plug in 1, I have 1 plus 3 plus 5, which is 9. And f prime of 1, well, that's 3 times 1 plus 3, well, 1 squared, but that's going to be equal to 1. So that is equal to 6. So the point that we have here is we have the point 1, 9. And at that point, f prime of 1 is equal to 6. So now when I'm looking for f inverse of 9, remember this is the y's of the original function. Y's of the original function, the x and y switch, so therefore that point is 1. Now I'm looking for the inverse of the derivative. Well, that's going to be, using the formula I gave us earlier, 1 over the derivative of the original with the function evaluated at that value, f inverse of 9. F inverse of 9 was 1, so 1 over f prime of 1 was 6. So if you think about it, what we found was, at this point 1, 9 on the function, we found our derivative to be 6. Now when I took and found the inverse, and I said that the inverse at the point 9, 1 now, because the x's and y's switch, the slope of the tangent line is the reciprocal. Okay, I got a little corny with this slide, but why do I care? Because I know this is all super fascinating and super exciting, but we also want to be able to find the derivatives of our inverse trig functions. That's going to be an important part of calculus for us. Okay, so we want to find the derivative of y equals the inverse sine of x. And pay close attention to this, because in your notes you're going to do the next one on your own. Okay, so looking at this equation here, I don't know how to find the derivative of that, but I know through my inverse properties that x equals the sine of y. Because if I were to solve this right side for y, I would get our inverse function. Now what we're going to do is we're going to take d dx of both sides. So when I take d dx of both sides, I have 1 equals derivative of sine is the cosine of y, but then I have that dy dx in there. So solving for dy dx, 1 over cosine of y. But I need this derivative in terms of x. So let's think about what we originally started with. We originally started with y equals the inverse sine of x. Remember, inverse trig, that's an angle, and this is the ratio at that angle. So my angle in a right triangle, theta, or instead of naming it theta, let's name it y. At angle y, our ratio for sine is x over 1. Using the Pythagorean theorem, we get the adjacent side to our angle y to be square root of 1 minus x squared. So now dy dx, what's the cosine of angle y? The cosine of angle y is adjacent over hypotenuse, or 1 minus x squared. So the derivative of inverse sine is 1 over the square root of 1 minus x squared. Now tangent. I want you guys to try and do this on your own. I don't ask this a lot of you. I don't ask this a lot, of you. So try this on your own. See if you can come up with what inverse tangent is on your own. And we'll go through this in class. Okay, inverse trigonometric derivatives. Please memorize these. The ones that you're going to see most often are inverse sine, inverse cosine. Since they're very similar, just cosine's negative. You can remember that because when we took the derivative of cosine, it was the negative of the sine. Tangent, hopefully you got that correct on the last slide. And then cotangent. Those are the 4 that I really want you guys to know. When you're going through the classwork, you can look up secant and cosecant either in the book or in your notes, but please make sure you have all 6 written down for me. And then don't forget your chain rule. If u is something other than, say it was inverse sine of 2x, remember you need to take the derivative also of that 2x. That's a composition of a function. Okay, find the derivative of y with respect to the appropriate variable. So we're finding d dx of this inverse cosine. So inverse cosine, remember that was the same as inverse sine, just the negative version. So 1 over square root of 1 minus 2x squared times by the derivative of 2x, which is 2. That's going to simplify to this. Our next example. Find the derivative of y with respect to the appropriate variable. Now we have two functions in here. We have x cubed times by the inverse sine of 7x. So our derivative of the first. Leave the second alone. Plus, leaving the first alone, derivative of the second, so that's 1 over square root of 1 minus 7x squared. And then don't forget the 7x is also a composite function, so we have our chain rule times by 7. So then simplifying, and I'm okay if you leave it like that. That is all we have for today. Please make sure that you submit your lesson summary on time.